A rare cometary visitor from beyond our solar system. This week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. We've spotted only 3 known interstellar objects, cometary bodies passing briefly through our solar system after long journeys between the stars. Bryce Bolin, a research scientist at Eureka Scientific Incorporated, has been part of the scientific teams that have studied all 3 of these objects. He joins us to share the story of 3I Atlas, the newest interstellar object, and how studying these fleeting visitors helps us learn about planetary systems beyond our own. Later in the show, Bruce Betts, our chief scientist, drops by for What's Up. He'll tell us about Comet Interceptor, a mission from the European Space Agency and the Japanese Aerospace Exploration Agency, designed to wait patiently in space, and then chase down a pristine comet or maybe even one of these interstellar wanderers. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. Before we dive in, I want to take a moment to ask for your help with an upcoming episode of Planetary Radio. Right now, I'm putting together a show focused on how cuts to grant funding are impacting students, researchers, and faculty in the space science community. While these budget decisions are happening in the United States, their effects are being felt around the world, especially by people that come to the United States to study or conduct research in space science and exploration. If you've been affected by these funding cuts, whether you're facing uncertainty, lost support, or you've seen your work disrupted, I'd like to hear your story. You're welcome to share a 1-minute audio or video clip describing your experience, which I may share on the show. You can introduce yourself or stay completely anonymous if you prefer. Just email your clip to planetaryradio@planetary.org. Your story matters, and together we can help others understand the real human impact behind these decisions. Now for our main topic of the day, 3I Atlas. For only the 3rd time in history, astronomers have identified a macroscopic object from another star system traveling through our cosmic neighborhood. These rare visitors that are called interstellar objects aren't born around our sun, but they're flung out of distant planetary systems before finding their way to us. The first one, 1I ʻOumuamua, arrived in 2017. I will never forget how exciting that was. The second one, 2I Borisov, followed in 2019. Now we welcome 3I Atlas. Discovered on July 1st, 2025, by the Asteroid Terrestrial Impact Last Alert System, or ATLAS, this new interstellar comet is visibly active, trailing dust as it flies into our solar system. Its reddish hue and extended coma tell us a complex story, one that hints at how it may differ from its predecessors. 3I Atlas is moving fast and growing more active as it nears the sun, so observers all around the world are trying to get a glimpse of it. To learn more, I spoke with Dr. Bryce Bolin, a research scientist at Eureka Scientific Incorporated, and the lead author on a new study describing the discovery and the physical characteristics of this interstellar comet. Bryce is one of only a few astronomers in the world who have studied all 3 known interstellar objects. His early work on ʻOumuamua helped characterize its elongated cigar-like shape. He later co-authored papers on 2I Borisov, including studies on its rotation and chemical composition. Now with 3I Atlas, he and his team are back at the forefront. Their paper titled Interstellar Comet 3I Atlas, Discovery and Physical Description was published on July 18, 2025 in the monthly notices of the Royal Astronomical Society letters. During the conversation, you're going to hear him refer to some of the images that are in that paper. I'm going to link to the images that he references along with the actual paper on this webpage for this episode of Planetary Radio. You can find that at planetary.org/radio. Hey, Bryce, thanks for joining me.
Hey, it's great to be here. Thank you for having me.
So you've had this really rare opportunity, which is that you've gotten to observe all 3 known interstellar objects during your career. What initially drew you to studying small bodies and then ultimately these interstellar objects?
Yeah, it's kind of a strange, I don't know, I guess you could say it's kind of a calling because I originally started out in physics, not wanting to do anything to do with astronomy. I was into high energy physics, particle physics. At the time when I was finishing up my undergrad CERN was starting to pop off with the Large Hadron Collider. And that was like the big excitement thinking, oh yeah, we're going to see all these crazy new particles with the LHC. And this is relevant for why I got to astronomy. I went to grad school, didn't go to grad school for high energy physics because it was like the height of the financial meltdown of 2008. And it was very hard to get into grad school. I barely got in. But where I wound up was not focused at all on high energy physics, which was a disappointment for me. So I went to school in Florida. Florida has this weird rule. Only one school in the state university system can have an astronomy program. But they had a program that was specialized in planetary science. So I was like, okay, I'm not doing the particle physics stuff, but why not try, planets? I didn't even know that was a topic you could study, right? So I kind of was like unofficially working with some of the planetary science faculty there. And through that connection, I got to go to France to a planetary science conference. And it was there that I kind of actually got set up with my first astronomy job. I met someone who was associate with people at where I did my master's, who was just happened to be looking for a research assistant for this new project that they were building in Hawaii called Pan-STARRS. And Pan-STARRS is this all-sky survey on Mount Haleakala that looks for asteroids. And it was also doing an all-sky survey, kind of like early Rubin Observatory kind of stuff, to look at galaxies and the other stars and other phenomenon. But the person who I linked up with for this job was specialized in asteroids. And it also turns out, this goes back to the grad school days, this person was also a former particle physicist. So it was really the connection with particle physics, because I didn't want to do asteroids and comets because I thought they were boring. Like, oh, they're rocks, right? So what got me into it was really this particle physics connection with Robert Jedicke at the University of Hawaii, where he came up with a way to parameterize the problem of using observations of asteroids and calculating the observational selection effects that go into the observations, which gives you an estimate of the inherent population before you have all these observational selection effects go into play. They do that in particle physics, and he found a way to apply this to asteroid observations from ground-based telescopes. And it just, wow, it was so fascinating for me. And I was at the University of Hawaii working for 3 years. It was actually, I was also working with Larry Deneu, who is the guy who discovered the 3I Atlas, the third interstellar object. I was working almost every day with Larry Deneu and Robert Jedicke and others at the University of Hawaii doing the discovery of near-Earth asteroids, potentially dangerous asteroids if they were to hit the Earth.
So how did you end up becoming parts of the teams that did the first observations on the first two interstellar objects?
That's an interesting story. That was also kind of an accident kind of thing. After Hawaii, I went to France where I did my PhD, which was another 3 years. And then when I finished that, I wound up at the University of Washington, which is where a lot of the Rubin Observatory work is being done. The director, Željko Izovich, is a professor there. The lead of the solar system processing team, Mario Juric, is also a professor there. And Mario was my supervisor while I was there. And at that time, the idea was that we were going to develop all these interesting tools to study asteroids at the Rubin Observatory. And then when Rubin comes on, to use those tools to study asteroids. But while I was there was also an opportunity to use this telescope in Apache Point called the ARC, the Astrophysical Research Consortium 3.5 meter telescope. Just on a side note, Apache Point is also where the Sloan Digital Sky Survey is hosted. And so there's a lot of collaboration between University of Washington and Sloan Digital Sky Survey. So they have access to this 3.5 meter there. And it was right after I started in the fall of 2017 at the University of Washington that, this ʻOumuamua first interstellar object was discovered. And at the time, I'd never really, I'd worked on survey detections of asteroids, and my PhD was on more dynamics of asteroids in the main belt. I'd never really done a case study, focus on one object study with ground-based telescopes kind of project before. But I had just this weird kind of feeling. It's like, wow, this is really cool. Like when the announcement of ʻOumuamua, the discovery of ʻOumuamua came out, I couldn't believe it. because I discussed interstellar objects with Robert Jeddick at University of Hawaii. He was one of the first people to study these things. He did the theoretical calculations to estimate how often you would see one based on actual data from pan-stars, using his expertise and synthesizing survey data to come up with an estimate of what the expected population is. But this is one a real bona fide thing, and I could hardly believe it. Had eccentricity of 1.17 or 1.19, might have to correct me there, but it was like significantly above 1. And for an asteroid to be bound to the sun, it has to have an eccentricity less than 1. And we've seen comets that are kind of weakly bound, just a little bit above 1, like hyperbolic, like 1.01, 1.05, but they usually have an encounter with a gas giant. And so we know they come from our solar system. They were just perturbed, which made them a little bit hyperbolic. But seeing something with 1.2, like 20% higher than 1, that was just like mind blowing. It was really startling. And it was like, wow, we talked about these things. And there were some estimates that it would take, like 5-10 years with pan-stars and like full power mode to see these things. But now we're actually seeing one. We see one. It's on our doorstep. It's here. And it's just like, wow, I just couldn't believe it. A body that formed in another star system coming into our system. It just was absolutely incredible. And we didn't know at the time, is it an asteroid or a comet? Is it like a kind of like something we would see from the outer part of our solar system versus something that's formed maybe more closer to the terrestrial planets or their equivalent in the exoplanetary system. So we didn't know. It was a huge mystery box. So I talked about it with Rob, and I thought, are people looking to study this thing? He's like, yeah, well, they're trying to hop on all the telescopes to look at it. And I was like, all right. So I went home. I remember lying down in the afternoon to like take a nap, and I just like couldn't get it out of my mind. Like, wow, this is an interstellar object. This is pretty incredible. So I wrote to the director or the assistant director of the Apache Point, who was a professor at the University of Washington, say, hey, do y'all have any telescopes that we could use to study this thing? It seems like it would be pretty important to try and study this object. It seems pretty interesting. And he was like, yeah, well, you can maybe try to work with Apache Point, 3.5 meter. I think we can probably get you some time for that. But you're going to have to work with this team from Johns Hopkins University. And it turns out one of the members of the team was the professor I worked with at University of Central Florida. His name was Jan Fernandez. And the other guy was this guy named Casey Liss, who was a longtime collaborator of Jan Fernandez studying comets. And it was Hal Weaver, senior professor at, I think, Duke University, and studying comets. So we collaborated and observing the first interstellar object ʻOumuamua with this 3.5 meter telescope. And the conditions were pretty good. We got pretty good data, and we were the first ones to assemble a complete light curve of this object. And to see it over its full 8-hour rotation, it had like this very large light curve amplitude of about 2 magnitudes. We were able to estimate the rotation period and the parameters of the light curve. It implies this very elongated shape, very large axial ratio. Our calculations were 6-1 because we came up with a way to kind of correct for geometric effects and shadowing effects on the asteroid. You would basically, if you assume without those effects, you get like an axial ratio of like 10-1, but we were more like 6-1 after you do this correction. So it was so bizarre that not only was it the first one coming from another star, it also had like some peculiar properties. We constructed this paper quite nicely, and it was pretty, I think, well received. So it was my first observational paper, and it was not bad. We talked about these things before, but we never thought, oh, it could be real. Like, it was so surreal.
But really, though, I mean, we know that these objects must exist and that they must come through our solar system at some point, but we're only now beginning to have the technologies to discover these things. And I think we're about to potentially discover a lot more because of tools like the Vera Rubin Observatory. Oh, yeah. It just objectively, even someone who has no understanding of what's going on in planetary science, I think this is one of those stories that just lights the imagination on fire, right? Like this, as you said, is one of our only opportunities to be able to really observe material coming into our solar system from somewhere else entirely. And I think people are right to be really excited about this.
Yeah, it's just, mind blowing, right? You have like all these theories about how many of these things exist out there and what their properties could be like, but like the difference between theory and what we actually observe can be quite large. So like for ʻOumuamua, we think it's most likely a comet because it has large non-gravitational perturbations like a comet. Have you heard the Queen song, Don't Stop Me Now? So there's like a really great line. Yeah, there's a lot of astronomical references in that song, by the way. It talks about like I'm on a rocket ship to Mars or something, or
on a collision course.
yeah.
Defying the laws of gravity. Yeah.
Yeah. So that line, defying the laws of gravity, is very scientifically based because astronomers in the 19th century were observing Halley's Comet. And they noticed that its predicted position from gravity only was very different from its true position in the sky. When they ran the calculations using Newton's laws and Kepler's laws to figure out where the comet would arrive next, it was off. And they were like, oh, it's defying the laws of gravity. They didn't know why exactly, right? But that line, defying the laws of gravity, that was in the Queen song, comes from the study of Halley's Comet, comes from the observation. Using a model where you only have gravity, only the laws of gravity, is not sufficient to explain the full physics of what's going on with the comet, which results in it having a position very different from where you would predict using only the laws of gravity. So defying the laws of gravity is what ʻOumuamua did as well. And comets defy the laws of gravity, and they emit gases which has a non-negligible momentum on their impulse on their trajectory. And so ʻOumuamua did this, and so there's some interesting discussion about that. But that kind of, let's say, eased some tension there because we weren't sure if ʻOumuamua was an asteroid or a comet, and because we think that comets outnumbered the asteroids by quite a lot in our star system, and star systems extrasolar, we think they should as well. You think that, what's going to be ejected into space and seen by some other people in the star system somewhere else in the galaxy is going to be a comet, but we didn't know. And so when ʻOumuamua was defying the laws of gravity, that kind of gave us a sigh of relief. The other two interstellar objects, 2I Borisov, 3I Atlas, are clearly comets. They have an active appearance, a tail, and some peculiar quality you see with that. They're both very different from each other in that respect. But they are comets. So it seems that so far, all the interstellar objects, they're comet-like material, which kind of checks with our expectations of planet formation and what we think the material around other stars should be like. But, we're in exciting times. We could see something asteroidal at some point. And because these are comets, they are basically hiding. The nuclei of 2I and 3 are hiding inside this envelope of dust.
What kinds of things have you been studying during the limited amount of time that we've known about the subject?
Yeah, so for 3I Atlas, we are first kind of look at it was using broadband colors, getting kind of optical wavelength colors. Also observed it with Keck telescope. We got near infrared colors and near infrared spectra. We want to understand the surface properties. Well, not really the surface properties, we've seen the coma, but like kind of the bulk, light scattering cross-section properties as a function of wavelength. And that tells us a number of things. We can see possibly the emission of cometary gases. In the visible and the near UV, you emit gases like cyanogen and carbon, diatomic carbon, triatomic carbon. And this can be indicative of the volatilization of the comet. You are producing these molecules that are first originating as ices in the comet, and then the heat from the sun is causing the ices to sublimate. And then they are undergoing these complex reactions while they're in the coma of the comet and breaking down. And one of those products can be cyanogen as well as the triatomic carbon. We're going to be getting some James Webb observations of these objects. I'm not formally a part of that team, but James Webb is going to be able to observe the comet in wavelengths well beyond the visible and near infrared. They go into the wavelengths into the 3 to 5 micron range, where we can start to see the emission of cometary gases directly from the volatile species that we see are most common among comets in our solar system, such as water, carbon dioxide, and carbon monoxide. And so we can do the direct detection of these gases using the James Webb. with Borisov, the second interstellar object, we did detect carbon monoxide using ground-based ʻOumuamua observations, as well as with the Hubble Space Telescope using the near UV instrumentation on the Hubble Space Telescope. But now we have James Webb. With Borisov and ʻOumuamua, we did not have James Webb, but now we have James Webb, and it has this great capability to study the volatiles of comets. So that's going to be potentially pretty huge. And they should be happening in a few days. We'll see if they get the comet.
As with anything that's like moving within our solar system, it's always tricky at a distance to try to like actually capture that thing. But I mean, those observations are going to be really wild. I mean, I don't know what the images themselves are going to look like, but the spectra of this object from a completely different system, it could be pivotal, especially given that we don't know where this thing came from. But some of the other things I've seen online suggest that this object could be much older than even things in our own solar system. What do we know about kind of where this object came from and potentially its origins based on that?
Well, this is a very interesting topic and something that I've thought a bit about. What people are doing with interstellar objects, 1I, 2I, and 3I, is they're basically estimating their kinematic ages in the galaxy. Basically, how, let's say, heated up or excited the orbits of these objects are, and the timescale in which it takes for them to get to this level of excitation. And they're saying that can occur, that would take billions of years for that to occur. If they were more recent ejection from the star systems, they would have orbits that aren't as heated up with respect to the galaxy. But my understanding is that this is actually pretty difficult to do. I mean, I'm not a galactic dynamics expert. With the discovery of ʻOumuamua, it became an open question. Okay, we're studying hyperbolic orbit with respect to the sun, but what is this thing doing out there in the galaxy? And it turns out that the galaxy is, well, I think everyone knows this, is quite complicated. It's a lot more difficult problem than asteroids orbiting our sun, in the sense that it's not like you have all the stars in the galaxy orbiting Sagittarius A star or the supermassive black hole. I mean, they do in a way, but there's the gravitational potential is quite variable in the galaxy because it's huge. And it can vary quite a bit because you have irregularities, you have molecular clouds, you have spiral arms, you have stellar clusters. And so the way that this affects the orbits of stars and interstellar objects as they float around the galaxy is quite difficult to understand. So when you're talking about things that are old, I think I saw some papers, some results saying, oh, these are billions of years old objects. But one orbit of the galaxy is like, 500,000 years for the sun. And so just in that time period, you can encounter spiral arms and all sorts of things that can really throw off your trajectory of the galaxy. And so I think it's really hard to say anything more than that past maybe one or two galactic orbits. So I think like people who are trying to backwards integrate these orbits to see, okay, when they were close to some star, they must have come from some star. I mean, it's a good idea. It's a like first order of curiosity thing to try and do. But it turns out the dynamics in the galaxy kind of prevent you from doing this accurately.
Yeah, everything's moving out there and everything's moving inside our solar system. I do want to say to people, though, who might be worried about this, that this new object, 3I Atlas, is not going to come close enough to Earth that we have to worry about it hitting us, even though it was discovered by Atlas, which predominantly looks for these kinds of things that might be a danger to us. Do we have a general idea of the way that this thing might be passing through our solar system?
Yeah, so I have a picture of the orbit of this object. So this is our paper that was published in the monthly notices of the Royal Astronomical Society, where we describe the orbit of this object. Now, so this is not the best orbital diagram in the world. I'm sure there's much more fancy ones out there that are animated and so on. But this is showing the orbits of planets in our solar system. The orbit of 3I Atlas is this black line right here. And Jupiter is this kind of khaki green line, and Mars is red, and the Earth is green, and Venus is blue, and Mercury is pink. So this was at the time the object was discovered on July 1st of this year. So the Earth is going to be rotating counterclockwise like this, whereas 3i Atlas is going to be going along this trajectory in this kind of bottom to top direction right here. So what's going to happen is 3i Atlas is going this direction, but the Earth is going to be rotating around this direction right here. So as you can see, it's actually 3i Atlas is actually going to get quite close to the orbit of Mars. So it could actually pass pretty close to Mars, which could be an interesting opportunity for spacecraft in Mars to try and observe this thing. I'm a fan of it. I think they should give it a try. 3i Atlas will be observable up until the end of August, early September-ish, and then it goes into solar conjunction because as it's getting closer to the sun, the Earth is going to be rotating around the sun, and the sun's at the center of this plot right here. The sun is going to be blocking the view of 3i Atlas from the Earth. So when it passes through perihelion, it will kind of be in what we call solar conjunction. But when the Earth gets around the other side of the sun, 3i Atlas will be going here. So we'll be able to see it again after it goes through perihelion.
And for people who are listening to this, since you can't see the plot, I will be sharing the paper and an image of this plot on the webpage for this episode at planetary.org/radio, so you can see. But it is very clear by looking at this diagram that this thing is on a wild trajectory, that it's just going to careen right out of the solar system. But also, I think what you've pointed out about the fact that we are limited in our ability in time to see this object from Earth is really interesting. And I love the idea of some spacecraft around Mars, or maybe even, I don't know, the JUICE mission or other ones that are out there right now, maybe even Psyche, to maybe, if they can, turn their cameras on this thing and see if they can get a look at it during the times that we can't observe.
That would be really interesting.
And since there's so much stuff coming out of this, it's got to be hard to figure out exactly what size the nucleus is on this thing. Do we have any size estimates?
So there's two ways of doing that. So at the present brightness of the comet, it's about 18th magnitude, 17th magnitude, and located about 3 or 4 astronomical units from the sun, kind of can give us an estimate of the nucleus, where we can compare that to other interstellar objects when they were observed at around the same time. They're not really the same because they have different amounts of dust in the proximity of the sun, but at the similar distance from the sun, 2i Borisov had a brightness that was a couple of magnitudes fainter. And we didn't detect the nucleus of Borisov. It was too small, but we think it's somewhere in the order of 500 meters, a few hundred meters. So when you have 2 orders of magnitude difference, that implies a size of about 1 kilometer for 3i Atlas. The other way of doing this is with high resolution imaging. So David Jewett at the University of California, Los Angeles, observed this object with the Hubble Space Telescope. The great thing about Hubble is that you have near diffraction limited observations from space that aren't affected by the smearing of the Earth's atmosphere. So from the ground, typical seeing is about 1 arcsecond. But in space, from Hubble, the resolution is about 0.04 arcseconds. So we're talking much, much finer resolution there. The reason why that's important for comets is because comets are resolved objects. So a point source viewed from the ground with 1 arcsecond resolution is going to be 1 arcsecond. When viewed from space, the size is going to be 0.04 arcseconds. But for comets, because of their extended sources, the angular size from the ground, for this case of 3i Atlas, is about 2 arcseconds wide. And in space, it's also 2 arcseconds wide. Key difference is in the nucleus region, because the nucleus is unresolved. The tail and the coma of the comet are resolved, but the nucleus is unresolved. So when you look at the comet from the ground, you're seeing a mishmash of the nucleus and the unresolved nucleus with the resolved tail. So they're combined on top of each other. And the scale of the mishmash for the comet nucleus is about 1 arcsecond wide. But in space, the tail is 2 arcseconds wide. It's just because it's a resolved object, but the mishmash with the nucleus is much, much smaller. And the cross-sectional area difference between 0.04 arcseconds from space versus 1 arcsecond from the ground is a factor of 600. So what that lets you do is lets you observe much closer in the nucleus to the comet by a factor of about 600. The reason why that's important is because you can basically measure the light from the nucleus with much less contamination from the dust. And it's a factor of 600 difference level in contamination. So when you're looking at a comet, it's kind of like looking at a fuzzy cat. Have you ever seen a big fluffy cat after it goes to the groomer and it gets like a buzz cut?
Yep.
So it's kind of a similar thing with comets. When I was a kid, we had a Persian cat, and my mom had allergies, so he would have to get a haircut. This big fluffy cat, and you get the lion cut, and it's got a buzz cut. It's a lot smaller. It's way smaller in cross section. And so using the Hubble Space Telescope to estimate the size of the cat or the comet versus the ground base, it's like a difference between just getting like a light haircut, like removing just a little bit of the fur from the ground, would be like the ground observation. You just give the cat a little bit of a trim here. But when you use the Hubble Space Telescope, you're getting the buzz cut. You're removing a lot of the hair. So you can get a much better estimate of the size of the cat. You need a higher resolution to shave most of the fur off and get a much accurate estimate of the size.
I'm just never going to think of a Hubble Space Telescope the same way ever again now. Thank you.
Yeah, it's like the cat groomer of space for cat comets. It's the ultimate space grooming tool.
We'll be right back with the rest of my interview with Bryce Bolin after this short break.
This October, NASA needs you. Hi, I'm Jack Corelli, Director of Government Relations at the Planetary Society. In response to unprecedented proposed budget cuts to NASA's science programs, the Planetary Society and a coalition of our allies and partners are organizing a special day of action to save NASA science. Join us in person on October 5th and 6th in Washington, D.C. You'll receive training on effective advocacy from our team of space policy experts. Then head to the Hill to meet directly with your representatives in Congress to advocate for protecting NASA's science budget and ongoing missions. If you can't come to Washington, D.C., you can still pledge to take action online. We'll give you the resources you need to be part of the movement to save NASA science. This event is open to any U.S. resident, no experience required. Space science benefits all of humanity. Let's stand together to protect it. Registration is open now at planetary.org/dayofaction. We'll see you in Washington.
Well, there's a lot of complexity to the way that comet tails behave. What's going on with the tail or tails on this object?
The 3i Atlas is quite interesting in the sense that the tail is kind of going in a strange direction. So here is the Hubble data of 2i Borisov, and it kind of has this extended tail that goes in the antisolar direction. So in this plot, I showed the direction of the sun as well as the direction of the comet in its orbit. But the really important one is the direction of the sun. So the sun is going in this southeast direction, and the comet tail is in the opposite direction of that. It goes out into space and to kind of the northwest. So that's kind of the key idea, is that comet dust, when it gets ejected in space, is blown in the direction opposite from the sun due to solar radiation pressure. But curiously, this is not what we see for 3i Atlas. So I'll show you my data here. There's much better data taken from the Hubble Space Telescope, but this is with the Palomar 200 inch over here. The key thing here is the sun direction is going off into the northwest direction. Curiously, the tail of this comet, it's blobby and is kind of preferentially going into the direction of the sun. It's going in the solar direction. So I discussed this in my paper. The interpretation is that you have large dust particles that are being ejected into space, and they could be large-ish. They could be, say, hundreds of microns across. If they're too heavy due to their size, they're too heavy to be blown in the opposite direction from solar radiation pressure. So I think what's happening is that the sun-facing side of the comet is heating up, and that is where the volatiles are coming off. And the solar wind is blowing in the opposite direction. But the dust particles, they're leaving the comet nucleus and they're going into space towards the direction of the sun. But the solar radiation pressure isn't strong enough to blow them around and go into the opposite direction again. So it's kind of giving the comet a little bit of a distended directionality towards the sun's direction. And the Hubble data show this really well because the Hubble data are really, really nicely resolved. And based on this information in my paper, we think that dust is leaving the comet at very slow speed, about a meter per second, very, 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 very low velocity. It seems to suggest that maybe the comet is kind of weakly active right now. It's a little bit further from the sun. It's starting to become active. It's starting to become more active. It's kind of it's not something like, whoa, like, unexplainable, but it's just not the typical thing that we see for a comet.
And all the more reason why we need to get as many observations of this thing while we can before it goes behind the sun from our perspective. Do you have any recommendations for people who might want to pull out their telescopes, or maybe if they're asteroid hunters, what can they do to try and help in the effort to understand this object?
Yeah, so I would recommend that they try to observe the comet in the morning hours before it goes into the solar conjunction. It will be available in the evening around end of August, as well as when it comes out of solar conjunction, early December or mid-November. It's predicted to be quite bright, around 12th magnitude. So that's within the range of smaller telescopes. It might be difficult to see with the human eye, like if you're looking through an eyepiece. But if you have like a CCD camera or a CMOS camera, I think it should be quite doable. I'm looking for ways to collaborate with the community. We're kind of putting together an observing campaign for this. Some people contacted me who have interest in working and studying this object. So if any listeners or people out there want to get involved, don't be shy. You can reach out to me and let me know. We can see what we can do.
Yeah, we only have limited time on this one, but they seemingly happen to come through our solar system on enough of a regular cadence that we're getting these opportunities every few years. And now with the Rubin Observatory and its ability to find objects, I was speaking with Stephanie Deppa from their communications team just a few weeks ago, and we were having this conversation literally days before this object was found. So I think people are going to have way more opportunities. But I mean, what does that feel like to you as someone who's kind of stumbled or random walked your way into a career full of these objects?
Yeah, so I think I think we're living in some really exciting times here. And it's interesting that 3I Atlas was discovered by a half-meter telescope in Chile, not more than 10 miles away from where Rubin Observatory is. So I think it's a pretty interesting sign here that things are accelerating towards more discovery of these types of objects. We had a little bit of a wait there because between the first interstellar object and the second interstellar object, we only had a 2-year period. And we had to wait 7 years for this other one right here, almost. And I think with Rubin Observatory, we can expect to find more, increase the search volume for these things. And it's going to be a wild time because we have to figure out, how we're going to study these things in the Rubin era, because Rubin is going to be detecting them much fainter. So 3I Atlas is very bright. It's a 17 to 18th magnitude is found by a half-meter telescope, by the Atlas telescope. But Rubin is a 6-meter equivalent telescope and detecting things much fainter than that, detecting things 23, 24th magnitude. That is going to be well outside the range of most telescopes. So far with this telescope, I've characterized it with, I use Keck telescope, which is a 10-meter telescope. But a lot of the characterization so far has come from smaller telescopes. Even for 8-meter telescope, 23, 24th magnitude object is going to be difficult to characterize. It will require photometry. Spectroscopy will be basically almost impossible. I think the majority will have to be getting photometry from the ground and then relying on space-based telescopes like James Webb to get the spectra, which is going to make James Webb more in demand for studying these types of objects. It'll be very interesting times. I think we'll see more discoveries, and I hope that the astronomical community will respond by accommodating more requests for the characterization of these objects. And I mean, looking very far into the future, with the ELTs, like the Extremely Large Telescope. Rubin is projected to have a 10-year operational lifetime. But if there's some overlap between the Extremely Large Telescopes and Rubin, those will be great for the characterization of these objects.
Between ELT and the Magellan Telescope we spoke about a few weeks ago, there's so many cool opportunities that are coming up. And I love that you've gotten to be at the crux of this new form of discovery. These objects are so cool and can teach us so much. And potentially someday we'll be able to rendezvous with these and learn even more. But that's even further in the future.
That's the dream. There's a mission called the Comet Interceptor, which has that as a goal. I don't know exactly when they're going to go into space, when they're going to launch, but I think it's within 3 to 4 years. But I'm thinking it's going to accelerate because of the discovery of 3I. I think it's going to accelerate that process. And I think there will be overlap between Comet Interceptor and Rubin Observatory. So I think you can expect, no guarantees, of course, but I think it's very realistic that we will have a Comet Interceptor rendezvous with interstellar object within the lifetime of Rubin. I think that's very, very viable.
Well, sometime when I bring you back on to talk about the next interstellar object you're studying, we'll see whether or not that's true. We'll play this clip and see what happens.
It could be very soon. It could be, 2 months from now. You never know. It could be a year from now. It could be 5 years from now. But I think we can expect 4I, the fourth interstellar object, to be in the not too distant future. I would say within a year or so.
Awesome. Well, I want to thank you for taking the time to do this. I know that you're currently at a Rubin workshop doing a bunch of work, but also I understand that after this object was detected, you spent something like 35 hours straight working on this.
Yeah,
and that is some dedication. Like I've had some long observing nights, but that is a long time. So
yeah. Oh my gosh. Yeah, that was wild. And nerd alert here. I was playing Magic the Gathering when I saw in the email that this was starting to come out. And so I was already organizing, making phone calls to try and an observing effort to get to telescope time on this thing. So we got time on it very quickly, July 2nd. When we got time on it, it was discovered on July 1st. So we got it on July 2nd with the ʻOumuamua telescope near Cairo. And July 3rd, we observed it with a Palomar 200-inch. And July 6th, we observed it with the Apache Point, a 3.5 meter. A day later, we submitted our paper. And we were working around the clock on this. And not only, my paper is about photometry, but there's a student I worked with at Caltech by the name of Matthew Belyakov. He was doing the spectroscopy. So we got photometry from imaging as well as spectroscopy. And so I was working on the photometry. He was working on the spectroscopy. And he has a paper, it's a research note of the American Astronomical Society. And he's working on a peer-reviewed publication in AAS journals to be submitted soon. But that was a very intense, a few days there. I was at one point sleeping for just a few hours on like some chair in the office there. But yeah, it was a race. In these cases, it is with the interstellar objects. The ʻOumuamua was a mad dash as well. When the discovery was made, it was around Halloween of 2017, and we jumped on it and tried to, got observations of it in early November and submitted our paper like a week later, like the second week of November, and posted it on the archive. And it's just every astronomer in the world who studies asteroids and comets is going to want to look at this thing. There's going to be big telescopes, Grand Telescope Canarias is one, this 10-meter telescope in the Canary Islands. You have the Keck Telescope. You have Gemini North, Gemini South, these 8-meter telescopes. You have the VLT. And, there's a lot of really good observers out there who want to pounce on these things immediately. And so if you want to survive in this kind of environment, you have to be very quick.
But seriously, may the coffee and the Magic the Gathering be with you as you do all of this work. I think a lot of people sometimes think that astronomy is really chill, very long scales between discoveries, especially in planetary science. It can be a long time before you can go back to another world and get a whole new set of data. But there are realms of planetary science and astronomy that are really, you make a discovery and everyone's on it in a hot second, and you are right at the crux of that. So I appreciate you putting in all the work, because I know how tiring that can be. But here we are learning all these amazing things about the third interstellar object we've ever discovered ever. It's crazy that we can even say that.
Yeah, well, it's just really exciting, and it's like, yeah, it's tiring, right? But it's the excitement and the adrenaline rush, just keeps you going, and a lot of excitement to be out there and try to be the first one to publish something on this. It's like, I don't know, I just couldn't stop until just kind of like the first interstellar object I was telling you about, how I wanted to take a nap, but I couldn't, and until I did something about it. It's kind of similar for me. I just want to like figure it out, and it's more exciting if you're the first person.
For a just brief moment there, you and the people on your team and the people observing this object around the world were the only people to know something deeper about an object that may have been traveling through our galaxy for ages. It's a fascinating thing to think about and a special place to be, and that you have a really cool career. And I really appreciate you taking the time to come on and share more about this. And seriously, when 4i happens, I'm calling you.
Oh, sure thing.
Well, thanks so much, Bryce.
Yeah, well, thank you.
Now it's time for What's Up with Dr. Bruce Betts, our chief scientist at the Planetary Society. Hey, Bruce.
Hey there, Sarah.
Right into the nerdy element.
Hey, I'm ready to go. Let's do a show. Okay, I'm done.
Nerd adjacent. So I was talking with our guest this week, Bryce, and he told me that the moment that he learned that this new interstellar comet existed, he was literally in the middle of a game of Magic the Gathering. I love that so much.
What action did he take?
Who knows? I mean, I'm sure like as soon as he found out, he just flipped the table.
Yeah, flip the table. People love it when you do that.
But it was the perfect opportunity. I've been playing that game since high school, and it was funny to me because on the day that we were having that conversation, it was literally the release of the first fully space set of Magic the Gathering, Edge of Eternities, excluding Unfinity and all of the commander decks that are space themed. So we got to have a fun, nerdy conversation about that. And I wanted to ask, like, have you ever played Magic the Gathering before?
I did, but it was many, many years ago with my sons when they were, not adults. And we did play and it was fun, but I haven't stuck with it like you have, obviously.
Wow, that's a really great way to teach math skills to the younglings. I mean, there's a lot of math there, man. The number of counters and tokens and like
I see.
Compounding factors.
Ooh, Magic the Gathering with compounding interest.
But if you are a fan of space games and you haven't played that card game before, I just want to shout out the beautiful space art on those cards. It's absolutely phenomenal. But another thing that came up in my conversation with Bryce was the European Space Agency's Comet Interceptor mission. And we didn't get to talk a whole lot about it in our conversation. Clearly, it's not launched yet. It's launching in 2029. But since I have you here, can you tell us a little bit about their mission?
Sure. It's a really cool concept because they're basically going to try in 2029 to launch a mission that will go out and just hang out until a comet's coming in that hasn't been to the interstellar system before. So it's coming from way out in the Oort cloud, and they have a spacecraft ready to go. And then when they find one that they can reach with the fuel they've got, they go after it. So they put it at Earth Sun L2, so 1.5 million kilometers away from Earth from the sun. And it hangs out there in some type of halo orbit, probably. And then it goes off to try to encounter either a long period comet or one of our interstellar visitors, which would be even trickier since there are fewer of them. But that would be super cool and super different, since even the long period comets have never presumably been altered by coming by the sun yet. So it gives a new opportunity. So it's a neat mission. And they actually even have 3 spacecraft, although they all travel as one until they get closer to the object. They've got a couple others besides the main one to do observations from other angles. And they will be like visiting something new, whether it's from outside the solar system or just way out in the solar system. And I should say it's ESA in collaboration with JAXA, the Japanese Space Agency, and is providing portions of it as well. So they basically have a good flyby type spacecraft, and they have the wherewithal to put it out there without an active target when they launch. And that actually will be very beneficial for trying to get to one of these things that there's no way we could just, well, there's no way, but there's no current technology easily done way to go hunt them once they come flying through and you've found them. Also, we find things farther out now as the telescopes and the search gets better. So there's more time to go after these things, either type of object, than there ever was before. Okay, shall we move into a
random space fact?
Let's do it.
Lunar football. One, a very amusing concept for a game that would be impossible to organize. Two, a nickname for the Apollo Lunar Rock 61016, which also has the nickname Big Muley, which oddly enough is the more official nickname. And Big Muley is the largest single rock and the most massive single rock returned by the Apollo astronauts. And it is roughly the size of an NFL football.
Wow.
Lunar football. It is 11.7 kilograms, which on Earth is 26 pounds, and 1/6 of that on the moon. It's a thing. I'll also mention the next two in size. We've got Great Scott and Big Bertha.
Great Scott.
Great Scott, which presumably I assume was named after Dave Scott, the Apollo 15 astronaut. Big Bertha is just a thing. Oh, I should say Muley, it was named after someone with a longer name, abbreviated to that, who is leading some of the geology activities on Apollo 16 and 17. Muley is hanging out with most of the lunar rocks in the curatorial facility at NASA Johnson Space Center, being kept all happy and pristine, as much as you can, so that researchers can keep applying new technologies to studying these things.
I've seen some smaller moon rocks, but just being that close to a piece of the moon. I know we get little pieces of the moon every now and again coming in as like lunar meteorites and things like that, but it hits different when you're right next to one of those Apollo rocks.
Yeah, it's pretty trippy. A little known fact, I did infrared spectroscopy of some lunar regolith way back in the past, so I was hanging out with lunar dust. That's what made me so crazy. All right. Everybody go out there, look up in the night sky, and think about gel cats, whatever that is. Thank you and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week with even more space science and exploration. If you love the show, you can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review or a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email, planetaryradio@planetary.org. Or if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members. You can join us as we work together to support the space science community around the world at planetary.org/join. Mark Hilverda and Ray Paoletta are our associate producers. Casey Dreyer is the host of our monthly Space Policy Edition, and Matt Kaplan hosts our monthly Book Club Edition. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. My name is Sarah Al-Ahmed, the host and producer of Planetary Radio, and until next week, Ad Astra.